This lecture is specific to Conceptual Physics AB, and it's a brief look at what is called the two-dimensional explosion. Imagine having, first of all, a horizontal frictionless surface, and then you have an object that explodes into three pieces. Okay, we're going to be given the details of the velocity vectors of two of those pieces after the explosion. We're going to then have to find the details of the third. Let's go ahead and turn this example immediately into a problem. Let me go ahead and read the problem to you, copy it down into your notes as we proceed. Okay, an object initially at rest on a horizontal frictionless surface explodes into three pieces, each of mass 1 kilogram, just to keep the situation as simple as possible. Okay, the first piece has a speed of 3 meters per second in the positive x direction after the explosion. The second piece has a speed of 4 meters per second, but it moves at a 90-degree angle with respect to the first. What is the speed of the third piece, and how much energy was released in the explosion? So begin to picture the problem in the following way. So right here the board will say, of course, is our horizontal frictionless surface, and then we begin with our three objects, like so. And there's some form of potential energy that is present here, such as spring potential energy, and that spring potential energy is released, and ultimately then the objects explode apart. This then means that later on, the amount of energy that's released in the explosion will be equal to the kinetic energy of the parts. But I'm getting ahead of myself here. Let's go ahead now and take a look at the details of the two pieces that were given after the explosion. So we're given that the first piece does the following. It moves off like so along the positive x-axis. So it has a mass m of a kilogram, and right here is its speed after the explosion. We'll call this v1. The magnitude of this velocity vector is given to us as 3 meters per second. Okay, and then we have the second piece, also of the same mass of a kilogram, but in this case we'll say it moves along the positive y-axis at a speed of 4 meters per second after the explosion. So then therefore that looks to say something like this, like so. So right here is the same mass of a kilogram. Okay, the speed of this piece here, call it v2, is 4 meters per second. And then we have the unknown third piece. Using a little bit of mathematical intuition on this diagram, into which quadrant do you suppose the third piece perhaps explodes into? Perhaps the third quadrant. In other words, perhaps the third piece does something like this. So right here is the third piece, also of mass m equal to a kilogram. Okay, the magnitude of this velocity vector is the speed v3. That's the unknown. Think of it this way. The total quantity of motion to begin with in this system is equal to 0 because all the objects are initially at rest here on this horizontal frictionless surface. Therefore, the total quantity of motion has to be 0 the whole time. Now here's then how we show this by setting up our conservation of momentum expression. So change in momentum of number 1 plus change in momentum of number 2 plus change in momentum of number 3 is equal to 0. And now what I'm going to do is just final minus initial, the initial momenta of each object and the final momenta of each object, and we'll come up with our expression. So first of all, for object number 1, it's going to have a final momentum here after the explosion that we'll just call P1, like so. And then minus its initial momentum before the explosion, which is 0, because the object begins at rest. And then we have the second object. Okay, after the explosion, it will have a final momentum we'll just call P2. And then minus the initial, once again, which is equal to 0, because the second object also begins at rest. And then lastly, we have right here the unknown. Its final momentum after the explosion we'll just call P3. And then minus the initial, which is once again 0, because the object begins at rest. And now let me just clean up this expression a little bit. Let me just toss away all of the zeros. So then therefore, when you do, you end up with this vector addition expression. Like so. This right here, think of this as the total quantity of motion before the explosion. Therefore, after the explosion, the total quantity of motion of the objects has to be the same because the sum of the external forces acting on the system is equal to 0. The momentum is conserved. So in other words, what we have here is vector addition, and the unknown is P3. The sum of the three momentum vectors, however, all of the MVs, has to be 0. So let's take a look at the first two momenta that were given. Right here is the P1, right here is the P2. Let's begin to add those together. Okay, so I have right here P1. And then using the tail to tip method of vector addition, I'm going to add to it P2. like so. However, when I add in P3, the sum of the three vectors has to be 0. So think of the origin as being right here on the diagram like so. So then therefore the third momentum vector, P3, must look like this. Like so. Notice that it has to point into the third quadrant on the diagram such that the sum of the three vectors, P1 plus P2 is plus P3 rather, is equal to 0 the whole time. Okay, now for this two-dimensional explosion problem here, all I'm forming is a right triangle on the diagram. So now let's go ahead and use a little bit of basic geometry with a right triangle to figure out what the P3 vector is. Okay, at this point on the diagram, by the way, I'm going to go ahead and replace all the P's here with mass times velocity. So let's go ahead and do that. I'm just going to erase here and write this as m times v1. This is m times v2. And this right here is m times v3. And then if I go back up to my momentum expression here, replace all the p's with mv. So mv1 plus mv2 plus mv3 is equal to 0. And now I can go ahead and cancel out all the m's from the expression. Remember that the masses are the same. So if I just now cancel out the masses from the expression on my basic triangle diagram, we now have the following. Like so. And then in order to find the speed, v3, all I have to do is a little bit of Pythagorean Theorem. Notice that the speed, the magnitude of the velocity vector v3 is just the hypotenuse here of this right triangle. But it does point into the third quadrant, the velocity vector itself. Okay, so doing a little bit of Pythagorean Theorem. We have here, for example, v1 squared plus v2 squared is equal to v3 squared. And now I just plug in the speeds and then we solve for v3. So right here is going to be 3 squared, first of all, which is 9, plus then 4 squared, which is 16. That gives me a total of 25. And then take the square root here. This is, by the way, v3 squared, like so. And then go ahead and take the square root here now to get v3 by itself. When you do, the speed v3 is 5 meters per second. So for those of you that already have some geometry under your belts, you may recognize this as a 3, 4, 5 right triangle. Okay, and then lastly, for part B of the problem, we're going to calculate now the energy that's released in the explosion. As I mentioned earlier, the energy released in the explosion is the sum of the kinetic energy of the pieces. In other words, some form of potential energy has transformed into kinetic energy during the explosion itself. So let's call the energy released E, and it's equal to the sum of the kinetic energy of the pieces. K1 plus K2 plus K3. Recall that kinetic energy is 1/2 mv squared. So then therefore, I have 1/2 m v1 squared plus 1/2 m v2 squared, and then lastly, plus 1/2 m v3 squared. And now nothing cancels out here or anything like that. All that I do is plug in all of my numbers, including the masses of 1 kilogram, and we end up then with a certain amount of energy released as in terms of joules. Okay, so let me just go ahead and calculate this. So this is 1/2 times 1 times 3 squared, and then plus 1/2 times 1 times 4 squared, plus 1/2 times 1 times 5 squared. And ultimately, after I calculate all of that out, I end up with 25 joules of energy released as the kinetic energy of the pieces in the explosion itself. So with respect to the two-dimensional explosion, all that we'll take a look at is an example like this, where the vectors form a right triangle.